Right, let's continue with the study of the carbonyl compounds. In the previous lesson, I explained what are carbonyl compounds and the difference between a molecule which contains the carbonyl group and the carbonyl compounds. And I say carbonyl compounds, what I mean by carbonyl compounds is aldehydes and the ketones, right? As for the other molecules, which carboxylic acids, esters, acid chlorides, amides, all those also have carbonyl group, but they are not classified to be carbonyl compounds. So all carbonyl compounds contains the carbonyl group, and not all compounds which contains the carbonyl group are carbonyl compounds. And I explained the aldehydes and ketones, their homologous series. I explained how to derive the general formula and how the aldehydes and ketones are isomeric to each other, and how the carbonyl compounds undergo nucleophilic addition reactions, and the variation of boiling points down the homologous series of carbonyl compounds was discussed in the previous lesson. That is, the boiling points increase as you go down the group, go down the homologous series, because the number of carbon atoms increase. The type of intermolecular attractions which exist between the carbonyl compounds is van der Waal forces, meaning the permanent dipole attractions, as well as induced dipole attractions. So together it's referred to as the van der Waal force. So as for the permanent dipole attractions, their strength does not vary much because number of polar groups are almost same, but the strength of the dispersion London forces increases down the homologous series. The reason being there increase in number of electrons. As the number of electrons increase, the strength of the dispersion force, the London force, increases down the homologous series. As for solubility, carbonyl compounds, low members are miscible with water. And as you go down the homologous series, the intermolecular force strength increases. As a result, the solubility will decrease. And also the carbon chain length, main carbon chain is a hydrophobic chain. It's a non-polar hydrophobic chain. That is also a reason why the water molecules cannot form intermolecular attractions with the carbonyl compounds as you go down the group, right? So solubility will decrease down the group, right? I think we drew the intermolecular attractions there. Did I explain the preparation of aldehydes and ketones? I think we should start from this point. Am I right? Okay. As preparation of aldehydes and ketones, there are so many ways to make aldehydes and ketones, but we have discussed one method in AS, that is the partial oxidation of primary alcohols, right? Primary alcohols is alcohol where alkyl group or attached to a carbon, where the OH attached carbon is attached to only one carbon atom, referred to as a primary alcohol. So you add acidified potassium dichromate or potassium permanganate acidified with sulfuric, and you heat and distill, not reflux. If you reflux, you get the carboxylic acid. If you heat and distill, you get the aldehyde, right? As for the ketones, you take any 2-ol, any secondary alcohol. You can oxidize in the presence of acidified oxidizing agent. Acidified with sulfuric acid, you can use KMnO4 or K2Cr2O7 and heat under reflux, you get the ketones. So this is how aldehydes and ketones are made. Please copy this. This is primary alcohol, and that is secondary alcohol. Yeah, ketones actually you have to reflux them. Distilling is not sufficient because even if you distill, then nothing happens. Oxidation will not take place if you distill the alcohol, secondary alcohol, because uh, you have to heat for some time for the secondary alcohol to oxidize. So if you just distill it, you will get the same secondary alcohol. So you need to heat on the reflux for some time to get the ketone. When you distillate the primary alcohols, you get the carboxylic acid. So you get the aldehyde. If you reflux, you get the carboxylic acid. So aldehyde is a product we discussed last week on the alcohols. Right? Aldehyde is produced as a result of partial oxidation of the primary alcohols. Right? So primary alcohols, how to oxidize partially? You add the oxidizing agent, acidified is sulfuric acid, and you heat and distill. You don't reflux it. If you reflux, you get the corresponding carboxylic acid. Done? Okay. So let's look at the reactions of carbonyl compounds, the aldehydes and ketones. The first reaction is a reduction reaction. We know the aldehyde is produced as a result of the oxidation of primary alcohols, and ketones are produced as a result of oxidation of secondary alcohol. So reduction is the opposite of oxidation. So if oxidation of primary alcohol gives aldehydes, partial oxidation of primary alcohols give aldehydes, reduction of aldehyde should give the primary alcohols. Likewise, the oxidation of secondary alcohols, if it gives if it gives ketones, reduction of ketones should give you secondary alcohols, right? So reduction is the opposite of oxidation, right? So as primary alcohols oxidize to aldehyde, the aldehyde can be reduced to primary alcohol. Secondary alcohol can be oxidized to ketones. Secondary alcohols can be, the ketones can be reduced to secondary alcohols. Now, as oxidation requires strong oxidizing agents, reduction also requires strong reducing agents. There are two reducing agents we can use. We can use lithium tetrahydroaluminate, LiAlH4, or sodium borohydrate. So if you take, say, aldehyde, when you use lithium aluminium hydride, of course, if you're using lithium aluminium hydride, you have to use in dry ether condition because lithium aluminium hydride is highly sensitive to water. It's highly sensitive to water. Presence of water, it gets destroyed. So lithium aluminium hydride should be dissolved in dry ether. Usually ethoxyethane. This is the ether we use, ethoxyethane, right? This is a reducing agent. You get the corresponding primary alcohol. You add H to this oxygen and H to this carbon. Reduction is addition of hydrogen. You add H here and H to this carbon. You break the pi bond, you add HH, right? So you get this. This is a primary alcohol. This reduction can also be achieved by sodium borohydrate. That's also a strong reducing agent. So either lithium aluminium hydride or sodium borohydrate can be used for the reduction purpose. And this is aldehyde. Of course, sodium borohydrate is very convenient to use because there are no restrictions such as lithium aluminium hydride. No dry ether conditions are required for sodium borohydrate, right? But for lithium aluminium hydride, you have to maintain dry ether conditions. And secondary, as for the ketones also similarly can be reduced to give a secondary alcohol, right? Secondary alcohol by either lithium aluminium hydride in dry ether condition, or can use sodium borohydrate. Either reducing agent can be used to reduce the ketones. So the same way you add H and H across the pi bond. You break the pi bond, you add H and H, so you can convert the ketone into secondary alcohol. This is reduction of the aldehydes and ketones to the respective alcohols. Now, why can't we use hydrogen for reduction? We know alkenes was reduced by hydrogen, right? So why can't we use such reducing agent where hydrogen is also a reducing agent? The reason is this lithium aluminium hydride. If you analyze how the reduction occurs, both lithium aluminium hydride and sodium borohydrate. This is lithium aluminium hydride contains the aluminium hydride ion, and sodium borohydrate contains borohydrate ion. These aluminium hydride and the borohydride ion reduces the hydrogen hydride ion. I mean, it produces hydride ion. Whereas hydrogen gas produces hydrogen ion, H plus ion. H plus is known as hydrogen ion, H minus is referred to as the hydride ion. So hydride ion is what reduces or what causes the reduction of the carbonyl group. The hydride ion, delta minus, attacks the plus delta carbon, and the carbon oxygen bond breaks heterolytically towards the oxygen, and this is how the reduction occurs. So carbonyl compounds contains a polar carbonyl group, therefore reduction is possible only in the presence of hydride ion. Hydrogen ion cannot be used to reduce this carbonyl group. You can notice hydrogen ion is positively charged. It will not attract the plus delta carbon of the carbonyl group. There will be repulsion, right? So that's the reason usually hydrogen cannot be used to reduce aldehydes or ketones, meaning the carbonyl compounds. So sodium borohydrate or lithium tetrahydroaluminate can be used to reduce aldehydes and ketones because these reducing agents produces hydride ions, H minus ions, which is utilized for reduction of the carbonyl group, right? So remember, using sodium borohydrate, there's no conditions, even presence of water is not a problem, but lithium aluminium hydride, if you're using, you need to use extremely anhydrous conditions because lithium aluminium hydride is destroyed in the presence of water. The carbonyl group in both aldehyde and ketone will be reduced in the presence of above mentioned reducing agents to give the corresponding alcohol, meaning lithium aluminium hydride or sodium borohydrate. Hydrogen will be added across the carbon oxygen double bond when heated under reflux with sodium borohydrate or lithium aluminium hydride. Ketones give rise to secondary alcohol, whereas aldehydes give rise to primary alcohols. The lithium aluminium hydride is used, it should be used in dry ether condition. Ethoxyethane is used. This is a formula of ethoxyethane, C2H5, eth, oxygen, ethane again. Ethoxyethane is a ether. Under perfectly anhydrous condition, as lithium aluminium hydride decomposes in the presence of water. Reduction also can be done in the presence of hydrogen nickel catalyst, but usually done in industry, not in laboratory, as the reaction requires high temperature. Now, you can use hydrogen nickel catalyst, but under forced conditions, the hydrogen can produce hydride ions when you force it under certain conditions, right? But that is, requires very high temperature and pressure to do that. So industry, in large scale reduction, there we use hydrogen nickel catalyst, but industry, because we can't use lithium aluminium hydride and sodium borohydrate in industry because they are very expensive, they're very costly. So using high temperature and pressure is actually cheaper than investing on lithium aluminium hydride or sodium borohydrate. Yeah. So hydrogen nickel catalyst requires very high temperature. Please copy these two reactions. So sodium borohydride will not reduce, or will only reduce carbonyl group of aldehydes and ketones, and not carbonyl groups of carboxylic acids or esters, unlike lithium aluminium hydride. Now see, this is very important. Uh, Aldehydes and ketones can be reduced by both lithium aluminium hydride and sodium borohydrate. But if you take other other molecules which contains the carbonyl group, like for example carboxylic acids and esters and acid chlorides, amides, reduction of those cannot be done by sodium borohydrate. You have to use lithium aluminium hydride because sodium borohydrate is a selective reducing agent, meaning sodium borohydrate can be used to reduce only aldehydes and ketones, right? But lithium aluminium hydride can be used to reduce any compound with the carbonyl group. It can be aldehyde, it can be ketone, anything with carbonyl group. But the sodium borohydrate can be used to reduce only aldehydes and ketones, right? So therefore, we call the sodium borohydrate as a selective reducing agent. So only aldehydes and ketones can be reduced, right? Sodium borohydrate has the advantage of being able to use in aqueous conditions, whereas anhydrous conditions are required as lithium aluminium hydride decomposes in the presence of water. The complex ion aluminium hydride releases hydride ions, which acts as a powerful nucleophile and attacks the plus delta carbon of the carbonyl group. Therefore, lithium aluminium hydride cannot be used to reduce alkenes. Of course, you cannot use, even hydrogen can be used to reduce alkenes as well as carbonyl compounds, but if you want to reduce alkenes, you cannot use sodium borohydrate or lithium tetrahydroaluminate because these releases hydride ions, and alkenes contains a loosely held pi electron cloud. Therefore, that welcomes only hydrogen ion. Hydride ion is already electron rich, so it will not get attracted towards the pi system of the alkenes. So alkenes can be reduced by only hydrogen and nickel catalyst, but not by these reducing agents, right? Because these reducing agent releases hydride ion, not the hydrogen ion. So H minus and the lone pair, the electron cloud of the alkenes, the loosely held electron cloud will have a repulsion. So therefore, it cannot be reduced using lithium aluminium hydride.